Human-Machine Interface HMI related to maintenance overrides, ensuring clarity, visibility, and control during temporary IPF bypasses. The Human-Machine Interface HMI plays a crucial role in the safe management of maintenance overrides applied to instrument protective functions, IPFs. During these periods, when a layer of protection is intentionally suspended, the HMI becomes the primary means by which operations and maintenance personnel maintain situational awareness. A well-designed HMI ensures that overrides are applied transparently, monitored continuously, and revoked promptly, without ambiguity or operational risk. Maintenance override visibility on the HMI is not optional. It is a safety-critical requirement. Clear, real-time presentation of override status protects against accidental process escalation, unplanned operation in unprotected states, and breakdowns in communication during shift transitions or troubleshooting. Core HMI features for maintenance overrides. Persistent display of active overrides. Any active maintenance override must be continuously visible on operator and engineering HMIs until fully cleared. Display should include IPF tag, affected device or function, override type, manual or automatic, reason for override, start time, and expected restoration time. Distinct visual indicators use standardized colors and symbols, e.g. amber or magenta indicators for override, flashing icons for overdue restoration, to distinguish maintenance overrides from process alarms or trips. Ensure uniform application across all display pages and control consoles. Alarm integration for override status. Active overrides must generate system alarms with appropriate priority. Escalation alarms should trigger if the override exceeds its approved time window or if an attempt is made to run the process at elevated risk. Operator interaction and restrictions. Read-only access for operations. Operators must be able to view override status but should not be able to apply or remove maintenance overrides unless specifically authorized. Activation and deactivation must remain restricted to qualified maintenance or instrumentation personnel through secure access. Confirmation dialogues and justification logs. If an HMI permits override activation, e.g. for automatic maintenance override switches, the interface must include confirmation prompts, justification entry fields, and role-based access control. Guided override workflow. Where applicable, the HMI should guide users through the override procedure, including validation of process readiness, selection of affected equipment, and expected actions after maintenance is completed. Communication and handover support. Override summary screens. Provide a centralized dashboard view listing all active overrides across the facility or unit. Allow filtering by area, function, SIL level, or time and override state to support shift handovers and maintenance planning. Override history and audit logs. HMI should provide access to logs of past override events, including user ID, duration, and comments. Integration with safety lifecycle tools ensures traceability and audit compliance, resilience, and fail-safe behavior. Override indicators must survive HMI reboot or failover. Any HMI redundancy or failure recovery must preserve and restore the current override status to avoid loss of visibility. Ensure HMI startup screens clearly reflect any IPFs that remain overridden. Override awareness on all relevant pages. Process-specific HMIs, e.g. compressor overview, reactor page, must include indicators for any overridden IPFs related to that area, not just in centralized dashboards. Conclusion. HMI is the operational link to override awareness. A well-implemented HMI is essential for managing the risks introduced by maintenance overrides. It ensures that protective gaps are never invisible, forgotten, or misunderstood. Through clear visual design, real-time data, and role-based interaction, the HMI empowers operators and engineers to remain informed, vigilant, and aligned during periods of intentional protection suspension. In high-integrity safety systems, effective HMI design is not simply a user interface. It is a vital layer of operational defense. Implementation of fire, gas, and smoke detection IPFs. Enabling early hazard detection for rapid protective action. Fire, gas, and smoke detection instrument protective functions Fs are critical components in the overall safety architecture of industrial facilities. These systems provide early identification of potentially catastrophic events such as hydrocarbon leaks, toxic gas releases, or fire outbreaks. so that appropriate automated or manual interventions can occur before escalation. Unlike process-based IPFs, which monitor measured process variables, e.g., pressure, temperature, these detection IPFs are environment-facing. They are implemented to detect abnormal atmospheric conditions and trigger responses such as area shutdowns, equipment isolation, deluge activation, or facility-wide evacuation. Given their role in protecting personnel and preventing large-scale damage, fire, gas, and smoke detection, IPFs must be implemented with extreme care, following disciplined engineering practices, field-specific standards, and robust lifecycle management. Core design principles for fire, gas, and smoke IPFs. Detection must be fast and reliable. The system must detect fire, smoke, or gas in sufficient time to trigger protective actions before conditions become life-threatening or damaging. Full coverage and sensor placement strategy. Detectors must be installed to cover all credible leak points, ignition sources, or accumulation zones, considering wind patterns, ventilation, and equipment layout. Placement must be validated through risk assessments, dispersion modeling, or detector mapping tools. No over-reliance on a single detector, redundancy or voting logic, e.g. 102, 203, may be required in high-risk areas to minimize false trips and maintain availability. Overlapping coverage ensures protection even if one detector fails or is under maintenance. Sensor types and selection criteria. Gas detectors may include catalytic, infrared, ultrasonic, or electrochemical types depending on gas properties. Selection depends on gas composition, leak rate, background concentrations, and required response time. Fire detectors include flame detectors, UV, IR, or combined, heat detectors, and rate of rise sensors. Choice depends on environment, fire type, open flame versus smoldering, and potential obscurants like steam or dust. Smoke detectors, typically used in enclosed spaces like control rooms, electrical cabinets, or HVAC ducts. Photoelectric or ionization types may be used based on fire development characteristics. All detectors must be certified for use in hazardous areas where applicable, with consideration for temperature class, ingress protection, and corrosion resistance. Response logic and integration with protective actions. Cause and effect logic. Detectors must be mapped to specific protective actions, such as gas detection leading to ventilation shutdown or flame detection leading to deluge activation. Logic must be deterministic, well-documented, and easily testable. Interface with emergency shutdown, ESD, and fire and gas systems, FGS. Fire and gas IPFs must be fully integrated into the site's ESD hierarchy, triggering partial or full shutdowns based on detection logic. Responses may include alarm activation, personnel alerts, unit isolation, blowdown, or emergency power cutoff. Time constraints and process safety time. The total response time from detection to final action must fall within the window needed to prevent escalation, considering flame propagation or gas cloud accumulation dynamics. Testing, validation, and maintenance requirements. Routine proof testing. All detectors must be tested at intervals defined by risk analysis and manufacturer recommendations to ensure sensor sensitivity and system response remain within specification. Testing must verify the entire loop, from detection through logic and final element. Calibration and environmental compensation. Calibration frequency should be determined based on installation environment, with additional attention to dust, humidity, and background gas interference. Override management during testing. Maintenance overrides must follow strict procedures with compensating measures and clear operator notifications to avoid unprotected conditions. Alarm management and operator interface. Clear alarm prioritization. Fire and gas alarms must be clearly distinguished from process alarms and given top priority on operator interfaces. Alarm messages should identify detector location, type of hazard, and time of activation. Visual and audible alerts. Audible sirens and beacon lights must be installed in affected zones to alert personnel with redundancy and zone-specific visibility. HMI and event logging. Activation events, overrides, faults, and test outcomes must be logged and timestamped for traceability and incident investigation. Conclusion: fire, gas, and smoke IPFs protect what process systems cannot. While process-based IPFs respond to equipment deviations, fire and gas detection IPFs guard against unpredictable external threats. Their implementation requires careful attention to coverage, sensor reliability, response logic, and integration with emergency systems. When designed and maintained correctly, these IPFs provide essential early warning and automated intervention, protecting people, assets, and the environment from fast-evolving, high-impact hazards that traditional control systems cannot foresee or manage. Testing of instrument protective functions, IPFs. Verifying that safety works when it must. Testing is a critical activity in the life cycle of instrument protective functions, IPFs, ensuring that each function will perform its intended safety action when demanded. Regardless of how well an IPF is designed, implemented, or documented, its effectiveness must be proven through structured, repeatable, and auditable testing. The goal is simple yet essential. Confirm that every component, from sensor to logic solver to final element, operates correctly within required timeframes and in accordance with the Safety Integrity Level SIL target. Testing is not a one-time event, but a recurring requirement throughout the life of the IPF. It supports commissioning, routine proof testing, diagnostics, post-maintenance verification, and periodic revalidation of functional safety performance. Objectives of IPF testing: confirm functional integrity. Ensure the full IPF loop detects the correct initiating condition and executes the expected response reliably and within the defined process safety time. Verify SIL compliance. Confirm that the actual probability of failure on demand, PFDEG, remains within the allowable limits defined by the SIL target based on failure data, test coverage, and interval. Identify hidden failures. Detect latent faults in sensors, logic solvers, or final elements that may not be apparent during normal operation but could prevent correct response during a real event. Support maintenance and continuous improvement. Use test outcomes to refine failure rate assumptions, maintenance strategies, and diagnostic methods. Types of IPF testing: proof testing, periodic test of the complete IPF to reveal undetected dangerous failures, typically performed offline or under controlled plant conditions depending on process criticality and safety impact. Partial stroke testing, PST, applies to final elements, e.g. shutdown valves, where full stroke testing is not possible during operation. Detects mechanical binding or degradation without affecting process flow. Function testing, used during commissioning or after maintenance to verify correct response from input to output. May involve simulation of process conditions, signal injection, or loopback checks. Diagnostic self-testing, performed automatically by smart instruments or logic solvers to detect internal hardware or configuration faults. Test planning and documentation. Test procedures must be standardized. Written instructions must define test scope, method, test equipment, acceptance criteria, and safety precautions. Test frequency determined by SIL requirements. Higher SIL functions require shorter test intervals to keep PFDAG within target limits. Frequencies must be documented in the Safety Requirement Specification SRS and maintained through a test schedule. Test coverage and effectiveness. Each test must demonstrate that the safety function operates as designed. If the test does not cover the full loop, the PFDAV calculation must be adjusted to reflect reduced test coverage. Test execution and field considerations. Isolation and permits. Testing often requires isolation of process conditions or equipment. Proper permits and communication with operations are essential to prevent unintentional trips or safety incidents. Simulations versus live testing. Where testing under live process conditions is impractical or unsafe, simulated inputs or virtual testing may be used, but only if verified to represent actual function behavior accurately. Operational constraints and bypasses. Any required overrides or temporary disablement of the IPF during testing must follow strict procedures with compensating measures in place. Recording and use of test results. Document all test outcomes. Each test must be recorded with date, responsible person, results, pass-fail, and any failures or anomalies noted. Failure investigation and response. If a test reveals failure, the root cause must be investigated, corrected, and documented before the IPF is returned to service. Performance trending. Over time, test records should be analyzed to identify trends in reliability, leading to better maintenance planning and potential design improvements. Conclusion. Testing confirms that protection is real. Testing is not just a compliance obligation, it is the means by which safety is proven. A well-maintained testing program ensures that every IPF remains fit for purpose, capable of acting when needed, and aligned with its design intent. By executing testing with rigor, documenting results accurately, and using the findings to improve system performance, facilities maintain the protective integrity that their people, assets, and processes depend on. Automatic testing of instrument protective functions, enhancing reliability through embedded, continuous self-verification. Automatic testing refers to built-in or system-driven diagnostic functions that continuously or periodically verify the operational integrity of components within an instrument protective function, IPF, without requiring manual intervention. Unlike manual proof tests, automatic testing operates in the background, detecting faults in real time, improving safety availability, and reducing the exposure window to undetected dangerous failures. When implemented correctly, automatic testing significantly enhances the overall reliability of IPFs by shortening the interval between failure occurrence and detection. It also reduces the burden on maintenance personnel, improves SIL compliance, and enables predictive maintenance strategies. Purpose and scope of automatic testing. Early fault detection. Identifies dangerous or degrading conditions before the next scheduled manual test, reduces risk of common mode or latent failures persisting unnoticed. Support for higher test frequencies. Enables continuous monitoring of key elements, effectively increasing the test coverage without increasing manual workload. Reduction in proof test interval requirements. Where automatic testing provides sufficient diagnostic coverage, the interval for full proof testing may be extended, provided it is validated during SIL verification. Common forms of automatic testing. Built-in diagnostics, found in smart transmitters, logic solvers, valve positioners, and field bus devices. Monitor for conditions such as sensor drift, power supply anomalies, memory faults, or communication loss. Heartbeat functions. Devices periodically transmit a heartbeat signal or status update, verifying that they are operational and responsive. Absence or degradation of heartbeat signals can trigger alerts or force diagnostics. Loop integrity checks. Logic solvers may monitor input and output consistency across IPFs and flag inconsistencies or unresponsive final elements. Partial stroke testing automated. Control valves can be partially actuated on a scheduled basis to confirm mechanical freedom of movement. PST can be triggered by the logic solver and automatically logged for maintenance review. Design considerations and safety impact. Diagnostic coverage must be quantified. Automatic tests contribute to safe failure fraction, SFF, and reduce the overall PFDAG, but only when their effectiveness is known, validated, and accounted for in SIL calculations. Non-disruptive operation. Automatic testing must not interfere with the process or cause spurious trips. Functions must be designed to perform self-checks transparently during normal operating conditions. Alarm and fault handling. Any failure detected during automatic testing must trigger a diagnostic alarm or visual indicator. If the fault compromises the IPF function, compensating actions, e.g. trip, bypass escalation, or controlled shutdown must be initiated. Integration with maintenance and monitoring systems, event logging and reporting. All automatic test results, pass, fail, or degraded, must be recorded and made available for review. Timestamped logs support compliance audits, failure trend analysis, and proactive maintenance planning. Interfacing with asset management tools. Automatic diagnostics can feed into plant asset management systems, enabling condition-based alerts, remote troubleshooting, and predictive analytics. HMI visibility and alerting. Operators and engineers must have access to automatic testing status via the HMI or maintenance interface. Alarms should be differentiated from process alarms to avoid misinterpretation. Limitations and complementary measures. Not a replacement for foolproof testing. Automatic testing increases reliability but does not eliminate the need for manual proof tests. Some failure modes, such as mechanical sticking, blockage, or long-term drift, may not be detected without physical verification. Requires secure and validated configuration. Changes to automatic test parameters must be tightly controlled, documented, and verified during SIL reassessment. Conclusion: automatic testing strengthens protection between manual interventions. Automatic testing enhances the reliability and responsiveness of IPFs by embedding intelligence and real-time diagnostics directly into the safety function. While not a substitute for comprehensive manual proof tests, it fills the gaps between test intervals, providing early warnings, reducing exposure to undetected failures, and supporting compliance with CL targets. When paired with rigorous engineering and maintenance practices, automatic testing becomes a powerful tool in the pursuit of continuous functional safety.